Thank you. In spirit of those fantastic lightning talks that we just heard, I'll hopefully give a lightning-fast tour of the lunar far side as viewed from Diviner observations. Diviner is a 9-channel push-broom mapping radiometer with 21 cross-track pixels, effective spatial resolution of about 200 meters, and that equates to a swath width of about 3.5 kilometers, so pretty narrow strips. And the channels span the visible to the far infrared, although for the purposes of this talk, we'll be focusing on the 3 channels near 8 microns, which were specifically designed to measure lunar surface composition. And the plot on the left here is showing thermal emission in a simulated lunar environment for various lunar soils, from feldspathic soils through mafic soils, and superimposed over that are the Diviner channels. The lunar environment actually changes thermal emission quite a bit from the terrestrial environment, and that does rely on needing to use a simulated lunar environment to have comparable measurements. This is mostly caused by vacuum-induced thermal gradients, but it's pretty complex. The end result is that you get a very strong Chris-Johnson feature, which is this mid-infrared emissivity maximum, and you get very weak Westralin bands, which are the typically diagnostic absorption bands at slightly longer wavelengths. The Chris-Johnson feature shifts to shorter wavelengths with increasing silicate polymerization. So as you go from olivine, that's at relatively long wavelengths, you go to pyroxene, that's shorter wavelengths, plagioclase is shorter, and quartz is shorter still. The Chris-Johnson feature is most sensitive to plagioclase and olivine abundance, and this is illustrated in the ternary diagram, which is plagioclase on the top, pyroxene on the left, and olivine on the right. You can see the plagioclase and the olivine have the unique colors and the strong gradient between the two, and the pyroxene actually does not have a unique color here. You could have a composition that is 100% pyroxene and it would have a similar signal in Diviner data to a 50-50 mixture of plagioclase and olivine. Fortunately, near-infrared spectroscopy is particularly sensitive to the abundances of pyroxene and olivine, so there's a really good synergy here. They can help us on this part of the scale, and we can really help them with plagioclase abundance because it's something we're very sensitive to. The bottom plot is showing a histogram of Chris-Johnson feature values for typical lunar terrains. It's a clear bimodal distribution with a Highland mean of around 8.15 microns, which is very, very similar to the Apollo 16 number we have, and Mari around 8.3 microns. We do need to apply a correction to our data to account for anisothermality caused by the extreme roughness of the surface and increasing solar incidence angle, basically at different temperatures within each Diviner pixel, and that causes the Chris-Johnson feature to shift to shorter wavelengths as you get away from equatorial noon. And at this point, we're using an empirical correction between radiance and incidence to shift individual observations back to a normal incidence. Just to demonstrate this quickly, this is Green Crater, which is an equatorial far side crater, and this is what the 8 micron temperature looks like without the correction. When you do the correction, you get a much more isothermal scene, and how this relates to the Chris-Johnson feature position. You have quite a bit of striping depending on when each observation was made, and when you correct it, you've eliminated most of that striping in some of the more extreme pixels. So the sites I'm going to be talking about today are starting with Goof Net Crater, then we'll move up to Compton-Belkovich, back down to Thompson Crater, and then we'll dwell for some time on Muscovancy Basin. So for each site, I'll be showing 4 different types of data. One panel will be from the WAC Global Mosaic, and this is an absolutely beautiful data set that I'm sure many of you are using. It allows you to not only see some of the albedo differences, but you get a good idea for the terrain and geomorphology. I have overlaid on the WAC Mosaic the Diviner rock abundance, and then I have Chris-Johnson feature values on a standard stretch for all of the sites, and then in the bottom right-hand panel, removing the topography, just showing the Diviner data itself with a stretch for each specific site. So the first site we're looking at is Goof Net Crater. This was a crater we identified last year as having unusual plagioclase composition in the southern and eastern part of the rim. Instead of being the typical AN94-ish that you see in the Apollo samples, this is something that has more sodium. So this is probably something on the line with bitonite, It could potentially even be as sodium-rich as labradorite, although we're still in the works on solving that. Carrie Downson has a beautiful poster describing some of the laboratory efforts that we're using to identify the plagioclase compositions. Compton-Belkovich is a site that we identified as having a high silica content in a similar manner to what we did for the near-side red spots that Tim Glotch reported on last year. It has either a high silica content or it has alkali feldspars. At this point, we can't make that determination, but it's still very interesting. Currently in press, Brad Jolliffe has a paper that describes Compton-Belkovich in beautiful detail, combining multiple data sets, talking about the geomorphology, and he is unambiguously shown that this is non-Mare volcanism on the far side. It has elevated topography, it has a series of small domes, and that's very exciting. Thompson Crater was identified as a location with pure olivine by the Kagoya spectral profiler data, and that was in the northwestern quadrant, so we'll zoom in on that. This red box highlights the area that the spectral profiler data showed had the pure olivine. When we look at it in the diviner data, we don't see a increase in the CF value to longer wavelengths, and this doesn't mean that there isn't olivine there. This just means that it must have a significant feldspathic component. And by looking at the Thompson feature values that we see here, we know that this actually must have a significant feldspathic component, probably greater than 50% and perhaps as much as 75%. And Jessica Arnold has a poster talking about some ways that you can get what the plagioclase percent is for the olivine-rich regions. I do want to spend a little bit more time on Muscovancy Basin. Beautiful image from the WAC map. Muscovancy Basin is, of course, interesting because of the unusual shape, has an unusually strong gravity anomaly, has a large area of mare in the center of the basin. As far as rock abundance is concerned, isn't particularly rocky. It looks pretty much like most of the moon does, and that means it's mostly fine materials. There is a small fresh crater to the northwest, and in the inner part of the basin on the mare, there is the typical constellation of very small impact craters. Of course, the reason that Muscovancy was of such interest to us was the M-Cube team identified 3 unusual rock types within a very constrained region of the western basin. They identified nearly pure olivine, orthopyroxene, and magnesium spinel in close proximity to each other. And this was written up by Carly Peters earlier this year. To summarize their results, these are the 5 sites they looked at. The uppermost was the olivine type site. The southernmost is the spinel type site, and then there's also an orthopyroxene type site. And then you have these really interesting areas where you have olivine and orthopyroxene in close proximity, and spinel and orthopyroxene in close proximity, but not overlapping. They are distinct morphologic units. When we look at the diviner rock abundance data, we don't see any rock anomalies associated with these sites, which is good. As Peters wrote in the paper, these sites are especially interesting because they know that they aren't just simply fresh impact craters that have dug into something and are exposing fresh materials, and that's definitely consistent with what we're seeing. With the diviner compositional data, we see that the spinel has moderate to long CF values. The spinel regions are indicated by the red arrows, and this is really interesting to us. We don't have a spinel in our thermal emission spectral library at this point that we've measured and simulated in the environment, but that's certainly something we need to add. Looking at the data that exists in literature using infrared reflectance, there's no evidence for there being any kind of spectral features across the wavelength range that we're looking at here, which is very close to 8 microns. The big emissivity maximum for spinel should be longward of 10 microns. And so don't quite understand why we're seeing a redness due to spinel, but it's very interesting and certainly something we're going to take a closer look at. The three orthopyroxene locations are indicated by the green arrows, and all of these were identified as being relatively pure orthopyroxene, although in the diviner data they actually appear quite different. The uppermost one has the most red in it, the middle one is more yellow, and then the bottom one is the least yellow, and this is an indication of how much of a feldspathic component is mixed with it. The uppermost one has values very similar to what we see for our laboratory pyroxenes, and so that must have a very small amount of feldspathic material mixed within it. And then by the time you get down to this bottom one, you have a much more significant component of feldspathic material, which actually makes sense because when you look at the map, you can see there's a small impact crater just to the east of the site that is bringing up more feldspathic material from depth and has probably put quite a bit of it into that adjacent site. And actually, to be perfectly honest, most interesting are the olivine. Olivine is indicated by the blue arrows. This site is fairly typical of what we see when we look at the near-infrared olivine observations. It has a rather Mari-like CF value, which indicates mixing with feldspathic materials of probably about 25 to 50%. And those are fairly widespread. However, this upper region is quite spectacular. This has CF values that are right in the range of pure forsterite in our laboratory measurements. And assuming that this isn't full 100 olivine on the surface of the moon, there's probably less than 10% feldspathic component. And this actually marks the most pure, the least mixed with feldspathic material olivine that we've seen in the diviner data. Zooming out just a little bit, we see that there's actually several more of these olivine regions on the northwestern part of the basin, and this is something certainly we need to look into more. So I'm actually ahead of schedule. That's great. So in conclusion, the far side has the full dynamic range of diviner data. We have areas that have high silica content, although they're not as nearly as widespread as they are on the near side. We have regions with potentially sodic feldspar compositions, and those are widely spread. And then you have the Muscovancy Basin with its unique lithologies. And the bottom line here really is that the diviner data set is rich and unique. It has the ability to measure the plagioclase abundance in these areas, which is something that's lacking from the near-infrared. But you really do need to rely on some of the near-infrared observations in order to figure out which areas are the pyroxene-rich areas and which areas are, which areas are the olivine-rich areas. So, thank you.
We have time for a couple of questions. And just to remind the speakers, if the people asking the questions don't have a mic, please repeat them so that the people grazing on the buffet in the tent can hear the questions. Apparently you've said everything there is. Oh. Yes.
Oh no, it's Brad.
Is there another area besides Compton-Belkovich? And do they correspond with the few modest thorium-enhanced spots?
No, that was definitely misspeaking. At this point, Compton-Belkovich is the only area that we have the clear evidence for the high silica materials. Some of these areas that potentially are the sodic feldspar areas need to be looked at a little bit more closely. They're not really identified with thorium elements, so we're not expecting it to be the silica-rich, but it could be more of the alkali-rich type of feldspar.